Hello, this is Michael Kogan. I am right now taking my exam 2. I'm working on problem 5 from a homework set. This is my second attempt. First one I did had no audio, so we made sure that it's fixed. This is pretty much on conductive spheres and insulated spheres, Gaussian surfaces, really. So the biggest thing is to know your theory. You'll be given most of the formulas. The formulas are pretty easy to apply, but you need to understand when and where to apply these formulas, right? That's the important part, to truly understand what you're talking about. So we'll hop right in for problem A. This is asking for a sphere of radius. We'll put this in big R. Radius of 5 centimeters. And a charge of positive 3 nanocoulombs, right? Coulombs. So when we're given this information, it wants us to figure out the electric field. So E1 and E2 of these surfaces at different distances, right? So one of them wants us to take it at 4 centimeters out, and one wants us to take it at 6 centimeters out. So here, let me pull up the formulas real fast, just to make sure we're all good. Okay, so like I said, one wants it at 4 centimeters out, so that'll be our E1. I'll put a little squiggle just so they're related, not equal. This one will be 4 centimeters. Related, not equal, at 6 centimeters. So first thing you want to point out is that, say this is our sphere, this is radius 5 centimeters, right? One point will be here that we're measuring at, and a different point will be here that we're measuring at. One's inside the Gaussian surface, and one's on the outside of the Gaussian surface, right? So for the inside of the Gaussian surface, we wanted to use the formula K. Now remember, that's the Coulomb's constant, so that's 1 over 4 pi times the permutation constant. That times Q of R divided by big R cubed. Right, so let me make sure we're using our constants correctly. Having the little r and big R can get confusing, but you just need to learn how to use them properly. So little r is going to be our distance. Sorry, my camera is kind of wonky. I have it on a bottle for us. But we'll want to plug in our values for that, so we'll pull over our calculator. And K, if you don't have it memorized yet, I don't know how that's possible, is 8.99 times 10 to the 9th power. And we'll have that multiplied against Q, which will be 3, times, hold on 1 second. It's also important for us to recognize this as a conducting sphere, obviously. Oh, sorry, no, this is an insulating sphere. My bad. Sorry about that. It'll be times R 5, or sorry, 0. I'm so sorry. Let me just reset this thing. 3 times 10 to the negative 9 times 0.03 or 0.04 divided by the radius, which is 0.05, and that'll be cubed. Sorry, my dog has those zoomies right now. And that will be 8,630 nanocoulombs. 130. 0.4, but we'll just round, obviously. And then we'll close the same thing, but it has a different formula for an insulating sphere on the outside. So we'll still have the same K constant, right? But instead, it will just be K times Q divided by R squared. That looks a lot more familiar, right? It's just the electric field of a charged particle afterwards. So we'll plug that in. 9 times 10 to the 9th power times the fraction Q, which is 3 times 10 to the negative 9, divided by 0.05 squared. And I made a mistake. I am sorry. This should be 6. You should always make sure you're plugging in the right things for each one. The R's are what always trips me up. So that's why I've been trying to show more that you should make one capital and one less. So our answer that we get is 7,491.666, right? But we'll round that off to 7,490 newtons per a coulomb, right? So then we have to move on to B. For part B, it says repeat part A if the sphere is a solid conductor. Okay, so this may seem like, oh, we just have to redo everything, great. But no, for a solid conductor, right, on the inside it's neutral. These are all neutral. All the charge is on the outside. So since E1 is measuring the inside, we know immediately that E1 is equal to 0, right? And on the outside, it's treated as just another particle, right? So we know that since it's treated like a particle insulator, that E2 is also 7,490 newtons per coulomb. All right, pretty easy on that part. A little bit of a trick question, but that's why it's important to remember the theory. All right. Next up is part C. Part C asks, you place a point charge -4 nanocoulombs, a distance of 9 centimeters from an infinitely long, thin wire and has a linear charge density of 3 times 10 to the negative 9 coulombs per meter. What is the magnitude of electric force that the wire exerts on the point? So, this may seem very daunting, but remember, these problems have been around forever. This formula is for every single one. So this is a very common formula. So actually on our formula sheet, we are given that pretty much immediately. Let me pull it up right here. Infinite wire charge per unit length, lambda. Distance r from the wire. All right, so we can see pretty much immediately that the formula that we're looking for to get the electric force, we need to get first the electric field that the particle is experiencing. So we'll say E equals 1 over 2 pi epsilon constant, right? Times lambda divided by r. And then after that, we just kind of have to plug and play. Since we need to remember that the Coulomb's constant is just 8.99 times 10 to the power of 9. We can just multiply that by 2 to cancel out the 4 and bring it down to 2. And then multiply that by the fraction of linear charge density, right? And the linear charge density, sorry, I should have written this down from the beginning. The original test charge, I'll write down Q2 for that, is -4 nanocoulombs. RT equals 9 centimeters. And lambda equals 3.00 times 10 to the negative 9 coulombs per meter. All right, so then we just plug in 3 times 10 coulombs per meter, right? 10 to the negative 9. Negative 9. And then we divide that by the distance. And the distance is 0.09. So the electric field at the test charge point will equal 599.3, and repeating, right? But we'll cut off there. Newtons per coulomb. Okay, and now if we want to get that back over to force, we'll recall the identity of E equals F over Q, or Q times E equals F. So then we just multiply that against our charge, which is 4 times 10 to the negative 9. And just like that, we get 2.4, 0 times 10 to negative 6. We actually got 2.3973, but remember, always round. Very important. And that will just be newtons. So we check that. That's all correct. All right, and then we go down to D. D is a word problem, multiple choice, right? It just says, is the force attractive or repulsive? So we can learn this by drawing a little graph. This is positive. We know that from its linear charge density. Okay. It's pushing upwards. Its field lines are going up, I should say. And here's a charge right here that is experiencing these forces. Now this charge is negative. And what happens when a positive and a negative interact? They attract each other. Right? So, or I should write that the other way, my bad. They want to pull each other towards each other, right? Negative go against the arrows on the field lines. So we'll say, with the obviousness of this, right, it is attractive. Okay, now down to part E. Oh, sorry, did I skip a part? No, sorry, I don't know my alphabet. That's why I am a physicist. All right. A point charge of Q equals 3.3 nanocoulombs is 8 centimeters. R equals 8 centimeters from an from a thin, flat, infinite sheet that has uniform surface charge density. The total electric field is 0 at a point halfway between the point charge on the sheet. What is the surface charge density of the sheet? Okay, so let's get another little drawing here. Kind of just helps you picture everything, right? So this is an infinitely long sheet. And one thing we can know about this is that you should know about this is that these infinitely long sheets are uniform all the way through. The electric field is the same all the way across. If you think about it, if you think about the square, the inverse square law, it makes sense why it would be. Because at a certain distance, it is still going to pass through, have the same amount of flux, right? All the way across. So it makes sense, right? And there is a formula to show us these infinite sheet charge with uniform charge per unit. The equation for the electric field produced by one of these, right, is E equals the charge density divided by 2 epsilon, the permutation constant. Okay. So we know that this is constant. As you can see in the formula, there is no R, so it doesn't change with distance. But what does change the distance is this electric field. And at some point here, 4 centimeters from the sheet, right, and 4 centimeters from the particle, that this is 0, which means that this cancels out that, right? That with this being positive, we're going to assume this one's positive too in this case. Since if it is negative, it just amplify it. So here it is at 0. So we want to figure out what the electric field is of the particle. And we can find that out easily enough by K times 3.3 nanocoulombs, or, times 10 to the negative 9 times 0.08 squared. Easy enough, right? So we'll pull our calculator. 8.99 times 10 to the 9 times 3.3 times 10 to the negative 9 times 0.08 squared. And then we get 4,000. That's correct, right? Yeah. Oh, I am so sorry. Nope, I made a mistake. I knew something was wrong. It needs to be halfway point. Halfway, not the full length. I even drew out a diagram, and I still didn't figure that out. Okay. And then it will be 18,541.9. I'll cut off there. Newtons per coulomb. Right. So then we want to figure out, since this is uniform all the way through, that means every point of this is like that. So we can just plug in this for that. Right. So we can rearrange the equation, E2 to equal 2 times epsilon naught. Right. And once we do that, I have to look up the epsilon. Or actually, I'm going to do a little bit of cheating here. I'm going to, since 2 over epsilon, oh yeah, I won't be able to do that. Sorry. I have to look up the epsilon constant. Epsilon naught value. It's called the permutation constant. It's very important. I should memorize it, but I just haven't yet. But either way, times 2 times, it is 8.85 times 10 to the negative 12 equals 3.28 times 10 to the negative 7. Right? And that will be I'm trying to think of the exact label for it. Coulombs per meter. That's it. Sorry, I just kind of blinked there. Okay. And then the next question, F, is asking us, is this positive or is this negative? Now let's go back to my assumption earlier, right? If this was negative, field lines would be pointing downward towards the object. And since we know this is positive, right? This is positive. We're told that immediately, right? If this was negative this way, every force that this would apply would only amplify it if it's between them, right? So this has to also be positive for it to be 0 in between it. So we'll write down just positive. Okay. And then we're on to our final one, G. Okay. G says 2 parallel conducting plates carry charges of equal magnitude and opposite charge. So one thing that we should already have in our mind looking at this is that 2 parallel conducting plates have the same effect as one infinite long sheet, right? It's equal throughout. The electric field is completely equal all the way through. With equal magnitude and opposite charge. When you place a point charge, Q equals 3.6 nanocoulombs between the plates, the force on the point charge is 22 micronewtons. What is the magnitude of the surface charge density on either plate? Okay, so let's first write down what we do know, right? QT equals 3.6 coulombs. And the force, Ft, equals 22 micronewtons. All right. So the first thing we want to do is we want to figure out the power of this electric field, right? That is the most obvious thing we want to do right off the bat. But first, let's look at why we do that. Sorry, I'm getting a little bit ahead of myself. The formula for the electric field of two plates that are between each other is E equals the charge density divided by epsilon naught, right? So now you see, right? This is why we want the electric field. If we have that, we can find this, right? But how would we find that? Well, there's a very easy way to. Remember, E equals F divided by Q, right? Because electric force is just the Coulomb's law divided by one of the charges. So, with that, we can find this super easily, actually. So, since we already have the force, it is. I need to make sure my handwriting is so terrible. I'm so sorry. Yeah, it is 22 micronewtons. Just want to make sure it wasn't like 2.2. 22 negative 6. And let me make sure I'm using my right conversion there. It's very important to always stay on your toes. You always make a mistake and it really backfires in the long run. But yep, it's negative 6. Divided by the charge of the particle, 3.6, and that's some nanocoulomb, so that one's easy to remember, negative 9. With that means that the electric field equals 6111.1, repeating. Right? And then we can use this formula, solve it for the surface charge density by doing E times epsilon naught equals surface charge density. So now if we can remember, right, 8.85 times 10 to the negative 12 times 6111.1, right, give a surface charge density of 5.41 times 10 to the negative 8. 0.41 times 10 to the negative 8. And that will be in coulombs per meter squared. Remember, area, it's different. Okay, but that's everything. Thank you for watching. This is just basically Gaussian physics. It's very simple, very elementary stuff, but it's prepping you more for more advanced, being able to derive these problems on your own. All right, thank you.